I will inform, sir.
Okay.
I think now you can start, sir.
Yes. Yes.
Yeah.
Yes. Yes. So some of you are coming late to the class after 9:05. I'm not going to let you in anymore. Okay. Only 5 minutes I can give. Okay. Guys, this is slip critical connection or also slip resistant connection or friction grip type connection. Okay. These are the different ways you can call. So I explained the theory behind it in the previous class. One of the students talked to me and said, he didn't have clarity on certain things. So just to clarify the matter, I'm going to explain once again regarding slip critical connection. See, whatever we have done until now is bearing type connection. Bearing type connection means here, if you look here, the side of the bolt is going to come in contact with the side of the plate. Okay, that means one surface is bears against the other surface. So as a result, the bolt may fail due to two possible ways. One is bearing failure, okay, and the other is shear failure. That means along this plane, because the bolt is in double shear, it will also fail along this plane. So there are two possible ways. But in case of slip critical connection, okay, so what happens is, so you can assume that there is no contact between the side of the bolt and the side of the plate. There is going to be some space throughout here. So what we do is we are going to introduce nuts, sorry, not nuts, bolts. Okay. Then we are going to tighten the bolt using the nuts so that the bolt will be subjected to tension. So once it is subjected to tension, so that is going to apply compressive force on these two plates. Okay. So once that is tightened to the desired extent, so if you apply force from outside, it may be compressive force or tensile force. So that tension in the bolt is going to create a frictional force of magnitude F, which is given by mu F multiplied by T, where T is the tensile force you applied for the bolt and mu F is the coefficient of friction between the surface of the main plate and the cover plate. Is it clear to you? In case it fails, that means if the joint slips, then it becomes bearing type connection. Is it clear to you? So if we take up the next example, sorry, the first example on this, I think it will be more clear to you. One second. So let us go through the problem. An ISA 100 millimeter by 100 millimeter 10 millimeter carries a factored tensile force of 100 kilonewton. So it is to be jointed with a 12 millimeter thick gusset plate. Design a high strength bolted joint when no slip is permitted. Then when slip is permitted, steel is of grade Fe410. See, this is an angle. ISA is Indian standard angle and having two legs of equal size. 100 millimeter is one size of the leg and the other is 100 millimeter. And the thickness of the angle is 10 millimeter. Okay. So one of the legs is connected to a gusset plate. Okay. That gusset plate thickness is 12 millimeter. And that angle member is subjected to a factored tensile force of 100 kilonewton. Factored tensile force is nothing but the design tensile force. One more name is ultimate tensile force to which the member is subjected to. Okay, that is 100 kilonewton. Because it is already factored, you don't have to multiply that value by 1.5, which is the load factor. Okay, so we have to design it by two ways. Okay, no slip is permitted. That means slip critical connection or slip resistance connection. And the point B is when slip is permitted. That means, so there is going to be contact between the side of the bolt and the side of the plate. Then in case of case B, we have to design the connection as bearing type connection by checking for both bearing and shear. Is it clear to you? So coming to the first case, no slip is permitted, and design a high strength bolted joint. See, whenever you design a slip critical connection or no slip permitted connection, then we have to use a very high strength bolt. Okay, so you cannot use 4.6 black bolts in this case, only high strength bolt. So that's why here what I have done is, so let us provide 16 millimeter diameter of HSFG bolts, that is high strength friction grip bolts of grade 8.8S grade. So 8.8S means take the first 8, okay, multiply that value by 100 to get the FUB value, which is the ultimate tensile strength of the bolt. Okay, and A and B is the net area of cross section of the bolt at the threaded section. Whenever you subject a bolt to tension, okay, it always fail along where the cross section is the least. Even though if you assume certain length of the bolt as shank and certain length as the threaded area, it will fail along the threaded area only because of the reduced area of cross section. That's why we need to consider A and B, that is the net area of cross section, which is equal to 0.78 times pi by 4 d square, where d is the diameter of the bolt. Okay, next coming to the plate. So the whether it is angle or gusset plate, what is the material it is made of? That is Fe 410 material. Okay, that is Fu equal to 410 Newton per millimeter square. So in this case, no slip is permitted. That means we are designing that as friction type of connection. So what we have to do is, so we have to find out how much friction each bolt can develop. So that is VDSF, that is design strength of the bolt in shear due to friction. So friction means it always acts parallel to the direction of the force. So we can call that as shear force as well. Okay. So coming to this is a formula we have. Where did we get this formula? Please open page number 76 of the code book. Please open it. So as we start doing the problems, we can discuss the code. So that is 10.4.3 slip resistance, page 76. I hope you are on that page. So if you go to the second column, it says VDSF equal to VNSF divided by gamma MF. So what is VNSF? VNSF is just below those three lines. VNSF equal to mu F Ne KH FO. So it's a matter of getting those values and substituting in the formula to get VDSF value. Okay, let us go one at a time. So in this equation, okay, what is gamma MF? So again, if you look at the code, so come below, you see gamma MF, that is equal to 1.10 if slip resistance is designed at service load, 1.25 if slip resistance is designed at ultimate load. So we are designing at ultimate load. Ultimate load is nothing but the design load or the factored load. So that's what 100 kilonewton is. So due to that, we should take gamma MF equal to 1.25 as recommended in the code book. Okay. Then what is mu F value? That is equal to 0.50. Here, mu F is not given in the problem. We have to assume certain value. So what I have done is I have assumed mu F equal to 0.50 as per table 20 on page 77 of the code book. Okay. If nothing is given, assume some sensible value. Okay. Then Ne equal to 1. That is number of effective interfaces. offering frictional resistance to slip. So how Ne equal to 1? If I go up, so in this figure, these two are the main plates, okay? And this is a butt joint, and these two are connected through two cover plates. Okay, when you tighten the bolt, there are two surfaces coming in contact with the main plate. That is this surface and this surface. Is it clear to you? These two surfaces. So when we do analysis and design, we have to consider only one half of the connection. Okay, and we are going to replicate the same thing on the other half. So coming back to this, there are two surfaces. These two cover plates are in contact with the main plate. Okay, but in case of the angle section, because it is connected to a gusset plate, so there is going to be only one surface of contact between the angle and the gusset plate. Okay, so if I go a little bit down, see, look here. So this is the gusset plate and this is the angle. So this is one of the legs of the angle, and the other leg is, you'll see two lines which is perpendicular to the paper. Okay, so there is only one face of the angle in contact with the gusset plate. That is the reason why I have taken Ne equal to 1 here. Okay, then what is KH? KH equal to 1. So in this case, that means if you go back to the code on page 76, it says KH equal to 1.0 for fasteners in clearance holes, 0.85 for fasteners in oversized and short slotted holes. Okay, 0.7 for fasteners in long slotted holes. So on what basis we took KH equal to 1.0? So if you go back to page number 73, table 19. If you go to the first column, it is serial number, second column nominal size of fastener, and the third column is standard clearance in diameter and width of slot. Okay, ours is the case of standard clearance in diameter. Okay, so for standard clearance in diameter, okay, so KH value equal to 1. Is it clear to you? Next, coming to FO value here. So FO as given in the code, it is equal to A and B multiplied by FO, where A and B is the area of cross section of the board at the threaded area. That's where we have the least area of cross section. If at all the bolt fails due to tension, it is going to fail along only the threaded area, and that area of cross section should be considered. Okay, and what is FO value? Again, it is given in the code book. So go to again page number 76. Okay, second column. So go down where it is given explanation for each of the terms: mu F, Ne, KH, gamma MF, FO, A and B, and FO, small FO equal to proof stress. Proof stress is equal to 0.70 FUB. Okay, so here for FUB, sorry, for FO, I have written 0.70 FUB. A and B is the area of cross section of the bolt at the threaded portion. Okay, then what is FUB? FUB is the ultimate tensile strength of the bolt. So what is that value? For HSFG bolt of grade 8.8, FUB value is 800 Newton per millimeter square. Okay, now we know all the values here. Substitute the values in this equation to get VDSF. So after substituting the values, I got the value of VDSF equal to 35.16 kilonewton. Okay, that means that is the design strength of each bolt in friction. Okay, but how many number of bolts we need? So the number of bolts we need is factored load or factored force, 100 kilonewton. That is the force to which this angle is subjected to. Okay, and the connection we design should be strong enough to withstand that 100 kilonewton force. That is strong enough means actually that is not the service load, actually that is the ultimate load. If at all it fails, so it is supposed to fail at 100 kilonewton. So this is the design force. So number of bolts we need is 100 divided by 35.16, that is equal to 3. We need 3 number of bolts. So we designed for the design load. So when we are applying the actual force to the member, it is always going to be 100, that is a factor load, divided by the load factor, which is 1.5. Okay, that is equal to 66.67 kilonewton. That is the maximum force to which the member is subjected to in reality. But when it comes to the design, we always go for design force or factored load. And this is the design strength of each bolt. So we get number of bolts. So with proper end distance, edge distance, and the pitch, you can provide 3 number of bolts. Okay. So just provide 316 millimeter dia H8.8 HSFG bolts. Okay. So that completes the first part, that is part A of the problem. Okay. Next part is when slip is permitted. Slip is permitted means, so even after tightening it accidentally or for some reason, so there is going to be a slip. Whenever there is going to be a slip, so the bolt here is going to come in contact with the side of the gusset plate as well as with the side of the angle. What it means is, I go up, if you look here, so when slip is permitted means there is going to be contact between this and the side of the plate. Similarly, there is going to be contact between the side of the bolt and the side of the plate. Then that becomes what kind of connection? It is going to become the bearing type of connection. In this case, we need to find out what is the shear strength of the bolt and also what is the bearing strength of the bolt. Okay. So coming back to the problem, when slip is permitted, that is, it becomes bearing type connection. Okay. And if we consider the bolt, if we consider what is the shear strength of the bolt, in this case, the bolt is in single shear. Remember, the bolt is in single shear because only one face of the angle is in contact with one face of the gusset plate. So if at all the bolt fades due to shear, it is going to be along only one plane. Therefore, the bolt is in single shear. So we have this formula VDSB equal to VNSF divided by gamma MB, where VNSB equal to FU by root 3 multiplied by NN ANB plus NS ASB, just multiplied by 1 divided by gamma MB. So where did we get this? Again, if you go back to page number 75 on the code book under 10.3.3, you will see that NN ANB plus NS ASB. So here NS, I'm going to take that as 0 because the shear, we assume that the shear plane is passing through the threaded area but not the shank area. So when it is not passing through the shank area, NS will automatically become 0. So we are left with only NN A and B. In this case, NN equal to 1 because the bolt is in single shear. A and B is the net area of cross section, that is the area of cross section of the bolt at the threaded level, which is 0.78 multiplied by pi by 4 multiplied by 16 square, where 16 is the diameter of the bolt. Okay. So what is FU? That is the ultimate tensile strength of the bolt, remember. So what is the tensile strength of the bolt? FUB value you need to substitute here, which is 800 Newton per millimeter square. We are using 8.8 grade bolt. So as a result, we got VDSB equal to 58 kilonewton. Therefore, bolt strength in shear, we got equal to 58 kilonewton. Similarly, bearing. So we need to check for bearing as well. So of course, we have this formula as per 10.3.4 on page 74 of the code book. Okay, sorry, page 75 of the code book. So VDPB equal to this, VNPB divided by gamma NB, where VNPB equal to this much, 2.5 kb DTFU. Okay, now we need to find out what is kb. So kb should be least of the following four values. So E divided by 3DO. So what is E value? That is the end distance. So E minimum value is 1.5 times DO or 1.7 times DO. E maximum is 12 T epsilon. So you can calculate those values separately. Okay, and you can write those values here. See, as I proceeded with the problems, so I'm giving less prominence to find out E. You know already. The reason is you know already. I don't have to repeat that part once again on how to find out E minimum and E maximum. That's why what I have done is I've simply taken some value which falls between E minimum and E maximum. You know how to calculate E minimum and E maximum. Similarly, pitch I have taken 50 millimeter, which falls between P minimum and P maximum as per the codal recommendation. Okay, so you don't get confused why I calculated E values in the previous problems, P values in the previous problems, but not here. Of course, I have calculated, I have given less prominence for this because you already know how to do this. So in the examination, you can find out E and you can find out P the way you know now. Okay, so with that, so I got the value E by 3DO equal to 0.55, where DO is the diameter of the bolt hole, which is 16 plus 2. 16 is the diameter of the bolt plus 2 millimeter clearance. Similarly, P by 3DO minus 0.25 equal to 0.676 FUB FU divided by FU. FUB is the ultimate tensile strength of the bolt, which is 800 divided by 410, 1.95 and 1.0. So we have to take least of these four values as kb value. So what is the least value? 0.55. Once I have this, so I'm going to substitute this value in this equation. So after substituting, I got 2.5, 0.55 here, and D is the diameter of the bolt, which is 16 millimeter, and T is the thickness of the thinner plate. So if you look here, so what is the thickness of the gusset plate? 12 mm thick. What is the thickness of the angle? 10 mm. Okay, when a bolt is pressing against this one angle and also against the gusset plate, okay, subjected to the same force, which one yields first? I think the angle is going to yield first because of the lesser thickness. So this thickness should be considered. So that is the reason why I have considered 10 as the thickness of the plate. That is thickness of the thinner plate. So here 12 versus 10. So 10 is the value. And FU value, that is 4. FU value is, if you look here, FU, again, bolt strength is 800 and the plate strength is 410 Newton per millimeter square. So 800 strength bolt is pressing against 410 Newton per millimeter square plate. So obviously plate yields fast. So that should be considered. So what is FU value for the steel plate? That is 410. So that is the reason I have taken 410 in this equation. Of course, this value is 1.25 and convert the whole value into kilonewton by dividing that value by 1000. So I got VDPB value equal to 72.16 kilonewton. So strength of bolt in bearing is 72.16 and the strength of bolt in shear is 58 kilonewton. So lesser of these two values is the bolt value. So lesser of these two values is 58 kilonewton. Okay. So what is the minimum number of bolts required? So 100 is the design force or design load in the member divided by the bolt value, we got 2. Okay. So if there is a slip failure, okay, you only need 2 bolts. If it is a friction type connection where no slip is permitted, you need 3 bolts. Okay. So if at all any slip happens here, so we are safe because we have already provided 3 bolts. But whenever slip happens, we know we need only 2 bolts. So that way we are safe. Is it clear to you guys? So with that, let us go with the next problem. That is a final problem on the bolted connection. Okay. So here it is 2 ISF sections, 200 millimeter by 10 millimeter and 1.5 meter long each are to be joined to make a member of length 3.0 meter. Design a butt joint with the bolts arranged in a diamond pattern. The flats are supposed to carry a factor tensile force of 450 kilonewton. Adopt HSFG bolts of property class 8.8, dia of bolt 20 millimeter, coefficient of friction mu f equal to 0.40, slip resistance designed at ultimate load. Remember this sentence, slip resistance designed at ultimate load. That means even here, even the slip is permitted. Okay, slip is permitted means we have to design for both slip resistance and also we have to design as bearing type of connection. That means if the slip happens, then it becomes bearing type of connection. So we have to check and we have to design for all the cases. Also determine the efficiency of the joint. Okay, that is the other part. So again, 2 ISF sections. So these are the 2 plates we have, that is Indian standard flat sections. Width is 200 millimeter and the thickness is 10 mm. What is the length of each flat? 1.5 meter length. But what is the length of the member we need? We need 3 meter length member. So we need to connect 2 flats, each of length 1.5 meter to make a member of 3 meter length to design or to withstand a design force of 450 kilonewton. Okay. So design a butt joint with the bolts arranged in a diamond pattern. So we have to arrange the bolts in a diamond pattern. You already know how to arrange the bolts in a diamond pattern. Okay. And of course, the flats are supposed to carry a factored tensile force of 450 kilonewton. Factored tensile force. That means PU value. You don't have to multiply this by 1.5. And bolt is 8.8 grade and 20 millimeter dia, mu f is 0.40. So remember slip resistance designed at ultimate load. Now coming to the solution. So what is the design load or factor load or ultimate load? That is 450 kilonewton. That is given in the problem. So when we consider the plates, so for plates, as usual, always you take Fe 415 steel for which Fu equal to 410 Newton per millimeter square. Coming to the bolt, for HSFG class 8.8 bolt, FUB is 800 Newton per millimeter square. So for 20 millimeter diameter bolt, A and B, that is the area of cross section of the bolt at the shank area. At this, not the shank, sorry, at the threaded area, it is pi by 4, 20 square will give you the area of the shank multiplied by 0.78. So the whole thing will give you the area of cross section at the threaded part or threaded portion. And mu f equal to 0.40, which is given. So whenever we are designing a connection, okay, here cover plates are not given, cover plates thicknesses are not given. So we have to find out. So based on thumb rule, so what we do is we are going to provide 2 cover plates, each of thickness 5/8 of thickness of the main plate, at least it says. So we have to give at least 6.25 millimeter cover plate on each side. But we don't have 6.25 millimeter cover plate in the market. So what we have is the next higher value, which is 8 millimeter. So provide 2 cover plates, each of thickness 8 millimeter. Okay. So shear due to friction. Then we'll find out what is the value. Shear due to friction. So VDSF equal to VNSF divided by gamma MF. So where VNSF is this. So find out all the values. So mu f is given already in the problem. NE equal to 2. Remember, in the previous problem, it was 1. But in this example, it is 2. The reason is we are giving 2 cover plates. As a result, 2 faces of the main plate are going to come in contact with the 2 cover plates. So there are 2 surfaces of resistance. That's why we take NE equal to 2. Okay. And for fasteners in clearance holes, KH equal to 1.0. Unless otherwise specified, you always take KH equal to 1.0. Coming to FO value, A and B FO. Okay. A and B FO is where FO equal to 0.70 FUB, which is given in the code book on page number 76 under 10.4.3. So what is FO value? 0.70 FUB. FUB is 800. Find out FO, 560 Newton per millimeter square. Substitute this value in this equation to get FO value, which is 137.2 kilonewton. Okay. Once we have this, so go and substitute all the values in this equation, to get VDSF. Okay. So that is these values. When it comes to 1.25, look here. So if you look here, gamma MF, whether it is 1.10 or 1.25. So again, if you look at the code book on page 76, it says gamma MF equal to 1.10 if slip resistance is designed at service load, and 1.25 if slip resistance is designed at ultimate load. Okay. So if you look at this sentence of the problem, slip resistance designed at ultimate load. Did you get it? Slip resistance designed at ultimate load. That means gamma MF should be 1.25 value. So that's why I have taken 1.25 here. Even if nothing is specified, you take 1.25. Okay. If it is specified, take the value accordingly. Okay. So once we have this, I got the value of VDSF equal to 87.8. Actually, this is not VDSB. This should be VDSF. So please correct it. Okay. And also we are designing at ultimate load. Slip is permitted. Okay. Slip is permitted. That means once the slip happens, so it is going to become bearing type connection. So then we have to find out what is the bolt strength in shear, and also we need to find out what is the bolt strength in bearing. Okay. So what is the bolt strength in shear? Fu by root 3 NNANB plus NACSB. We assume that the shear planes are going to pass through the threaded area. So that's why NS equal to 0. Here NN equal to 2 because the bolt is in double shear, because we are giving 2 cover plates. So once we are giving 2 cover plates, there is going to be double shear multiplied by A and B 245. This is 1.25 and divide that value by 1000. As far as FU is concerned, this is for the bolt. So FU value for the bolt is FUB, which is 800 Newton per millimeter square. So whatever given in the code is little bit confusing. Sometimes it is FU, there it is FUB, FU for plates. So whenever you consider the value, think generally, take the values in context. Okay, understand the concept and take the values accordingly. FU is not 410, it is FUB value, which is 800 Newton per millimeter square. So this is the strength of the bolt or design strength of the bolt in shear. Similarly, let us go to bearing. Again, E40, P60. See, this is the way you are going to do in the examination. Okay. So in the previous problem, I skipped these steps and I have taken the values directly. Okay. In the examination, you do all these things. So find out what is E3DO, that is 0.60. P by 3DO minus 0.25, that is equal to 0.66. And this is 1.95 and 1.0. So least of those four values is 0.60. So that is the value of KB we need to take in this equation. Next, D is the diameter of the bolt, and T is the thickness of the thinner plate. So in this case, that is 10 mm I have taken. 10 mm because if you look here in the problem, so we are connecting two plates. 1 second, I'll go here. So 10 mm I have taken here because I'm connecting two plates of thickness 10 millimeter. Okay. And I'm providing two cover plates, and the thickness of each cover plate is 8 mm. So what is the combined thickness of two cover plates? That is 16 millimeter. 8 millimeter plus 8 millimeter, that is equal to 16 millimeter, and the main plate thickness is 10 mm. Take lesser of those two values, so which is 10 millimeter. That's why I have taken. Then FU value is 410 because bolt of strength 800 Newton per millimeter square is pressing against the plate of 410 Newton per millimeter square. So when two materials of different strengths are pressing against each other, so the material with lesser strength will yield fast. So in this case, what is the material with lesser strength? It is a plate which is 410 Newton per millimeter square. So that value should be considered. So that is the value I have considered here. Finally, I got VDPB equal to 98.40 kilonewton. So now I have three values. One is this value, that is the friction value, 87.8. This is the shear value, 181.1. And this is the bearing value, which is 98.40 kilonewton. So out of those three values, take least of those. Okay. So what is the least value? That is 87.8 kilonewton. Once I have the least value, that is the bolt value. Therefore, minimum number of bolts required equal to 450 divided by the bolt value. 450 is the design force in the member. So I got 6. Even if you get, say, 5, for example, you have to make this 6 because out of 5 bolts, you cannot make a diamond bolt set. So you need at least 3 bolts or 6 bolts to make the connection as diamond bolting. So anyway, I got the value of 6 through the calculation. So I'm going to provide that. So this is the way I have provided. Is it clear to you? So 6 bolts, 3 here, 2 here, and 1 here. Similarly, on the other side, again 6 bolts, 3 here, 2 here, and 1 here. So, and provide proper pitch, that is transfer pitch, and proper longitudinal pitch. Okay, end distance here, and the edge distance, proper edge distance and end distance as per the codal recommendation. So once this is done, so the design is not complete. The design is not complete. We need to check the safety of the connection. So as a result of drilling bolt holes, okay, so the plates may fail. Okay, that is, cover plates may fail, and also the main plates may fail. Okay, we have to make sure that the plate strengths, that is both cover plates and the main plate strengths, are greater than 450 kilonewton. Okay, so for the main plate, section 1.1 is critical. That means if at all the main plate fails, that fails along section 1.1 only. If at all the cover plates fail, so they fail along 2.2 only. Okay, this is the shape of cover plate. See, this cutting is done. Okay, ignore it, or else even if you want, you can show this as complete. Okay, don't get confused with this cutting. Okay, So what we need to do is we need to check what is the strength of the main plate along section 1-1 and what is the strength of the cover plates along section 2-2. So strength of the joint due to bolts is, of course, bolt value is 87.8, okay, multiplied by 6 bolts. So that is the strength of the joint, 526.80 kilonewton. So we are going to make use of these values when we calculate the efficiency. Now, so for time being, don't worry about this. So we'll find out what is the strength of the main plate here and what is the strength of the cover plates in this section 2-2. So main plate, section 1-1 is critical for main plate. So what is the tensile strength of the main plate? That is 0.90 AN Fu divided by gamma ml as per 6.3.1 page 32 of the code book. So if you consider this line, there is only one bolt hole. So to get the net width of the plate, total width minus the diameter of the bolt hole. So that's what we should consider. So if you look here, 200 is the width of the plate minus N is the number of bolts that section 1-1 cuts. It cuts only one bolt. DH is the diameter of the bolt hole. Okay. So multiplied by the thickness of the main plate, multiplied by 410, that is the tensile strength of the main plate divided by 1.25. And this 0.90 is the value given in the code book. Okay. So what is the main plate strength, which is 525.46 kilonewton. Okay. So what is the design force in the member? That is greater 450 kilonewton. So this design strength of the main plate is greater than 450 kilonewton. So that way we can guarantee that the main plate is not going to fail due to tearing of the plate. Similarly for cover plates. Okay, same formula we are going to apply, and section 2-2 is critical. So when you take section 2-2 here, so along these two lines, how many bolt holes we have? So we have 3 bolt holes. As a result, from this width, we need to take out 3 bolt hole diameters to get the effective width of the cover plates. So that is B200 minus 3 times 22, where N is the number of bolts along section 2-2 multiplied by DH, that is the diameter of the bolt hole, okay, multiplied by T. T is the combined thickness of the cover plates. We have 2 cover plates, remember. So each of thickness 8 millimeter. So the combined thickness is 16 millimeter. That's why I have taken 16 millimeter multiplied by 410 divided by 1.25. Of course, divided by 1000. So we got this value equal to 432.90 kilonewton. Okay. So this is also greater than 450 kilonewton, which is the design force. That way, so we can say that even the joint is not going to fail due to the failure of the cover plates. So that is also safe. So then what is the strength of the joint? Strength of the joint is the least of the above values. So 6 bolt values and strength of the main plate, that is the design strength of the main plate and the design strength of the cover plates. So take least of those values, and that is the strength of the joint. Okay, this strength of the joint is of course greater than 450 kilonewton. So we are okay with that. Okay, now next thing is we need to find out what is the efficiency of the joint. Okay, so efficiency of the joint in case of chain bolting, if you remember, so we considered only one pitch width. In case of diamond bolting, we should not consider only one pitch width. The reason is, so from pitch to pitch, number of bolts vary. For example, if I go back up, so look here, if I consider this width, okay, of pitch, one pitch width, so we are going to come across one bolt within that width and also half bolt here, half bolt, that is 1.5 bolts. So if you take a pitch here, we are going to come across 2 bolts. So which pitch you are going to consider? That is a problem. So for that, whenever we come across a diamond joint, okay, we consider the whole joint. Okay, so what is the strength of the whole joint? This is the strength of the whole joint. Next, we need to find out what is the strength of the solid plate. So what is the solid plate? 200 millimeter is the width of the solid plate and 10 millimeter is the thickness. So solid plate means we should not deduct any bolt hole values. Okay, so the strength of the solid plate is 590.40 kilonewton. So what is the efficiency of the joint? Again, I repeat. So when it comes to diamond bolting, we are not considering one pitch width because number of bolts for each pitch width varies. So we are not going to get the right value. So that's why we should consider the whole joint. Therefore, efficiency of the joint eta equal to strength of the joint, which is 525.46 divided by strength of the solid plate, which is 590.40 multiplied by 100. So we got the efficiency value eta equal to 89 degree. So this joint is really efficient. So always remember, so diamond bolting is the best way of bolting because that joint is very efficient. Is it clear to you guys? So is there any doubt? So with this, so we are coming to the end of bolted joint connection. Of course, there is another part called bracket connection, so which I am not going to cover. So I will come back if time permits. Okay, or else I'm going to give you notes. If I keep covering that part, it is going to take very, very, very long time. Then we are not able to finish the syllabus properly. So for time being, I'm going to skip that part. Okay. So starting from tomorrow, I'm going to start with the design of welded connection. Okay. Once the welded connection is over, so this module, I think you are pretty much safe. Okay. So welded connection is not going to take too long. So it is so conceptually, if you understand a little bit clearly, then everything will be okay. Is it clear to you? Okay, guys. I hope everything is clear to you now. So if you have any doubt, you can ask me right away. Guys, any doubt?
No, sir.
So who said no? No
Nachiket.
doubt? Hmm?
No, sir.
So you followed.
Yes, sir.
So the first question is, were you sitting in front of the computer for the whole time? I'm
Yes,
just
sir.
joking, man. I'm joking. Okay. Oh, who is that? Yes, that is. Speak again.
Nachiket, sir.
Okay, that is Nachiket. Okay, 18CV060. Okay. Okay, guys, thank you. Thank you and be safe. Stay home and we'll meet tomorrow. Thank you.
Thank you, sir.